So this topic is about finding the highest power in any given factorial, finding the highest power of a prime specifically in any factorial. So in mathematics, sometimes it makes sense to understand a concept, not from the basics, but try and develop the concept from an example, try to see how it works, and then get to the whole complete concept, give it a more general meaning, give it a generic look. So we'll try and understand this concept from this particular point of view. So when I say highest power in a factorial, let's be more specific. So highest prime power in a factorial, because if we cover this case, then we have covered all the cases as it is. So let's take an example where this concept might be useful. Okay, let's consider something like 27 factorial. So the question is, the 27 factorial is a very big number. Okay, and how many zeros exist at the end of this number? Meaning, if I can write this number as something into 10 power something, what is the max value of this? To take a shorter example, let's consider 5 factorial. 5 factorial is 120. So it has 1 0. The same way, 27 factorial has how many zeros? So that is what we're going to cover here. So let's first try and understand the question. So the question is asking us to find out how many zeros exist at the end of any given factorial. So it makes sense for us to understand where a 0 comes from in a factorial. Let us just consider the small example itself. 120 is 1 times, 2 times, 3 times, 4 times, 5. Okay, and the 0 that we're talking about comes from multiplying 2 with 5. That's where we get a 10, and that 10, the 0, is what ends up being here. Now that we've looked at a small example of it, so we can draw this conclusion saying, hey, if we have a factorial, every time a 2 gets multiplied with a 5, I'll have a 0. That's the only way you can have a 0. So when we consider a very big factorial, we have to pick out all the 2's that are there in the product and all the 5's that are there in the product and see how many pairs we can make out of them, thereby figuring out how many zeros can come at the end of this thing. So it's very easy to understand that if we consider 27 factorial, the number of 2's that exist in 27 factorial, or any factorial for that matter, because 2's keep repeating with a frequency of 2, like 2, 4, 6, 8, all have a 2 in them, right? And the 5's keep repeating with a frequency of 5, 10, 15 and 20 and so on, 25 and so on. So because of the higher frequency of 2's compared to 5's, any factorial, you can make a statement something like there will always be more 2's compared to 5's, which means the limiting thing is the number of 5's that we have. So instead of focusing on how many 2's are there, if we are able to catch how many 5's are there in 27 factorial, we can pretty sure find a 2 for each 5, thereby we will be able to get the number of zeros. That is a simple understanding that we have here. So let's try and understand how many 5's are there in 27 factorial. So if we keep writing 1, 2, 3, so on, there is a 5 there, and 6, 7, so on, there is a 10 there, so on, so on. There's a 15, there's a 5 here, so on, 20. And there's a 25, so on, and that's it. So we basically have 1, 2, 3, 4, 5 5s, and if we can observe, this is 5 square, so there's one more 5 here, okay, not just one. So there's 1 5, 1 5, 1 5, 1 5 here, and there are 2 5s here. So I can add 5 plus 1 and say there are 6 5s. So there are 6 5s in the product of 27 factorial, and you can easily find 6 even numbers within this 27 factorial, and each even number will have a 2, and this 5 will get multiplied with the 2, thereby giving you a 0. In short, what we are trying to say is this 27 factorial will have 6 zeros. So this is the concept. Note that we have easily been able to count the number of 5s, albeit in a crude manner, but we understand what is going on here, and we were very careful not to miss an extra 5 that was coming from 25. Okay, so this whole process that we have now executed, because mathematics sometimes streamlines all this into a nice short looking formula, we can also say 27 factorial, the highest power of 5 in 27 factorial can be written in this form, where the square brackets represent the greatest integer function, which, as we all know, the greatest integer function of any number yields a number that is yields an integer that is less than or equal to the number. For example, this is 1 point something, and this is point naught naught something. Okay, so this is an ongoing series. So greatest integer function of 5.4 is 5, greatest integer function of 1.08 is 1, and everything that follows after that would obviously be 0, 0 point anything, 0 point higher powers and all of them would be 0. So you end up getting the same 6. And if you observe, it's very easy to observe here that the 5 that we obtained here, 5, 10, 15, 20 and 1 5 we picked from 25, is the exact 5 we are getting from here in this manner. Okay, and it's very easy to understand when we are like dividing 27 with 5, we are counting how many 5s are there of the type 1, single 5s. Okay, and we are rounding off to the lower number so that we get that number, and the same procedure we are repeating it with the higher powers. By saying 27 by 25, we are counting how many 25s are there in the number, so I can have one more 5 from that. Okay, and the same concept continues to higher powers also. So this is the concept which tells us that in 27 factorial we have 6 zeros, which can be obtained in short if we write it in this manner. So now, to make a statement, if this idea is understood, from where it has come and how to easily obtain the answer in a quick manner, but you're not compromising on understanding. We are very well understanding where this thing is coming from. So once this is understood, it's very easy to generalize it and write a generic formula for this whole idea. So now if we consider any number, let's say n, n factorial. The highest prime power p in n factorial is given simply by the expression greatest integer function of n by p plus greatest integer function of n by p square plus greatest integer function of n by p cube and so on indefinitely. Whatever this expression we have, like we have just seen in the case of 27 factorial, will yield the highest power of that particular prime p. Let's take a quick example. For example, if we consider the same 27 factorial and you are required to find out what comes in this box, like what is the highest power of 2 that is there in 27 factorial. We can easily obtain it this way: 27 by 2 greatest integer function plus 27 by 2 square, which is 4 greatest integer function, plus 27 by 8, which is 2 cube, plus 27 by 16 plus 27 by 32, so on. So this would be 13.5, 13. This would be something 6.75, so it will be 6. This is 3 point something, so it will be 3. This is 1 point something, this is 1. This is again 0, and once the 0 start, they keep going. So you quickly add it in no time to figure out that you have 23. So the highest power of 2 in 27 factorial is 23. The same concept can be extrapolated to take it to the next level. For example, what if I don't pick a prime? What if my question was in 27 factorial, what is the highest power of 12 we have, which is not a prime? What is the highest power of 12 we have, which is not a prime? So what we do here is just break this number into, prime factorize the number. Okay, and because it is made up of these primes 2 and 3, figure out what is the highest power of each one of those primes. For example, 27 factorial we have just figured out can be written as 2 power 23 into some number. Okay, we have just seen that. And the same 27 factorial, we have to figure out what is the 3 power. And if we quickly do that here alongside, we will figure out that 27 factorial, the highest power is 27 by 3 greatest integer function plus 27 by 3 square plus 27 by 3 cube, so on. So this quickly turns out to be 9 plus 3 plus 1 plus 0 and so on, which is 13. So 27 factorial has a 3 power 13 and a 2 power 23. Now in order to figure out how many 12s you can make out of it. So to make a 12 you need a 2 square and you need a 3. There are 13 3s that are available, and how many 2 squares are available? Because 2 is, there are 23 2s available, you can say there are about 11 2s 22, 11 2 squares that are available. So there are 11 2 squares that are available and 13 3s that are available. So we pick the least number here and say for all these 11 2 squares we can have easily arrange 11 3 powers, and we will be able to say the 27 factorial, the highest power of 12 that we have is 11. So the answer is 11. So what we have covered is we have understood where this particular formula comes from, how it is derived, how it is intuitive, and once we figure out how this formula comes from, how can we apply it in a wide array of applications, whether it is the number of zeros that are there at the end of a number, or whether we have to find out what is the highest power of any number, need not be a prime, highest power of any number as a matter of fact within that particular factorial. That brings us to the end of this concept.